We're going to continue our discussion of primes in this video and talk about the fundamental theorem of arithmetic eventually, but I kind of want to jump off from that last theorem that we saw in the video. And that theorem said, you know, if we have for p a prime and n a number that can be factored or represented as a times b, what that really allowed us to say was that, well, we could look at n as a times b, right? But we could also say that, well, since p divides ab, we could represent n also as p times k for some k in integer. Okay, so it's a different factorization. Okay, but now this is really interesting. So what we can do with this new second factorization is say, well, according to this theorem that we saw, again, we could say that there exists a prime that divides this. So let's say that there exists a P1 such that P1 divides PK. Okay, well then we can say that N, or that we can do the same sort of trick and say that, well, P1, since P1 divides PK, we can say, and we're going to assume for a minute that P1 and P are different. So, and specifically, so we could actually modify that P1 divides K, but if you want to leave that in there, it's not going to hurt. So then we can say that, well, according to this, we can say that K is P1 times K1 for K1 an integer. Okay, and then so then when we think about our number n overall, we can say that this is going to be, well, a times b, but we can also say that's p times k, but now we can actually factor that further as p times p1 times k1. Okay, and then we can apply the same old idea that I just did up here to k1 and get this as like p times P1 times P2, K2, and so on and so forth. And you can continue breaking it down into primes. Okay, and so that really leads us into what we think of as the fundamental theorem of arithmetic. Okay, and so this just says, okay, we have a number that's bigger than 2. Okay, we can say that this can be factored into a product of prime numbers. Okay, and so there's P1, E1, P2, E2, etc. P1 are the distinct primes, and then the E1 through ER are the exponents on each of the primes, so the number of times these primes appear. Okay, and then the other interesting thing is that the factorization ends up being unique. Okay, and so this is something that you saw way back in Algebra 1 and 2, maybe even earlier. And so now we're just going to go ahead and prove it using formal mathematics. Okay, so the proof, well, I'm going to kind of say that I'm going to do a little hand waving and say, well, the A is equal to the product part is an extension of our idea above. So I'm not going to, I would write it out formally, but that'll take time, and I think you can kind of piece together the argument from where we left off from above. But what I do want to focus on is this idea of unique factorizations. Okay, so now when you encounter these types of arguments in mathematics, there's a typical procedure that you go through. And that procedure is really to say, well, if you want to show things are unique, it can't have two forms. So you start by saying there exists two forms of the factorization in this case, or two forms of this thing that you want to eventually show are the same. Okay, so let's kind of discuss that. Okay, and I'm not going to necessarily include all the formal language, but I do want to get into at least some of the major mathematical ideas. So what you would begin by saying is that, okay, A can be represented as P1, P2, P3, product, ... times P to the s, okay, or p sub s, you can pr, it doesn't really matter which subscripts you use. And then this is also, so a can also be factored as q1, q2, q3 up to qt, and I think mathematicians like going with qt just because it's, well, funny. But now, okay, so if we have this sort of thing going on, right? So what we can do is say, well, this is a factor, or these are two different factorizations. We know that P1 must divide A, so this is kind of the next step. P1 divides A, right? So then P1, oops, let's see that again. So then this implies that P1 divides Q1, Q2, Q3 up to Qt. All right. And then you can say that by this general idea, this means that P1 divides some Qi for, and I'll just say for some I. Okay, right? So if it divides A, it divides the other factorization, therefore P1 divides Q1. But then remember that that these are all primes, right? But P1 Qi, and if it's easier for you to give this a number, that's fine. And actually, I think for our purposes, it is. So let's just say, assume Qi is equal to Q1. And this is going to help us with note taking. And again, you can rearrange this, so whatever. R prime. Okay. So then we have, okay, so if those are both prime, then that cancels out the factors, or cancels out those two factors, so you would be left with P2, P3, ... PS, yep, is equal to Q2, Q3, ... Qt, okay? And then you repeat this, and eventually you are going to get one of the sides, and assume for right now that assume that s is less than t. You're going to get 1 is equal to qts minus 1, or qt minus s, and then times qts minus s minus 1, actually plus 1, I'm sorry, ... up to qt. And then, so this is just showing that the product is 1, meaning that, so then all these are just 1, and then it follows that if this is all 1, then you can really say that s is equal to t, because otherwise you just have a bunch of products that are 1. So this implies that s is equal to t, and therefore the two factorizations are the same up to rearrangement. Okay, so again, just to reiterate, for unique factorizations, assume two different ones, then you work with one factorization, and you'll continually divide out all the primes from both sides, and they have to divide because they're the same factorization of a number, so they have to divide, and then you just kind of repeat that division process until you're left with one side as 1 and the other side, if you have a product as 1 and you're working with integers, the only way that they can, the only way this can be true is if all the remaining factors are 1, which then gives you that s is equal to t. And then your factorizations are unique up to rearrangement. All right, so that is our proof of the fundamental theorem of arithmetic. So now we have the ability to say, hey, we take a number, factor it into its primes, and there we go. In that factorization, when we're talking about the exponent, okay, and I'll just highlight this, the exponent, that exponent you can call it the exponent. Otherwise, there's some other language that we typically use with this, and that's just the order of p, whatever prime we're talking about in A. And so there's just some of this notation. And so just as a quick example here, we have this incredibly large number, 588,245,000, which is really just 2 to the third times 5 to the fourth times 7 to the sixth. And yes, I came up with that factorization before making this video. And so now, just to demonstrate this idea of the order, it's really just the exponent. So this, we would say it's the order of the prime 2 of this number, and that is just going to be the exponent of 3. And then the order of 5 of this number is 4. And then the order of 7 is 6. All right. So this just was a nice video proving a fundamental theorem of arithmetic that we've known for quite a while, and maybe taken for granted. So imagine what other theorems that we've taken for granted that we can now start to prove in higher mathematics. In the next video, we'll be kind of extending this our discussion of primes and talking about multiplication and multiplicative inverses.